is the two pathways. You have oxidative pathway, okay, oxidative pathway, oxidative pathway, all right, and the other one is like, which is like irreversible, meaning like you cannot go back, and that is up to like your ribulose 5-phosphate, all right. When you do go back, just make sure you go back. That's oxidative pathway, irreversible pathway, and other one is like non-oxidative pathway, but that's reversible. Remember how like from the ribulose 5-phosphate, like we make those ribose 5-phosphate, and we also made like xylose 5-phosphate, right? And those from we combine together and we make cellulohaptulose 7-phosphate, and we also made like a glycerolaldehyde 3-phosphate, right? And then from there we added with the transaldolase, and we made like erythrose 4-phosphate, and from that we also made fructose 6-phosphate, and we also combined xylose with like again the erythrose 4-phosphate, and we made fructose 6-phosphate, and also we made glycerolaldehyde 3-phosphate. Those pathways I just mentioned, these are it's not oxidative, it's not non-oxidative, but it's going to be reversible, all right? But from this pathway, like this leading towards and up to like ribulose 5-phosphate, right? That is going to be my non-reverse. It is oxidative because we're removing electrons, but it's going to be irreversible. Just letting you know, all right? Okay, now, role of the NADPH is very, very important, guys, because the role of NADPH is dependent on where the NADPH are present. That is something that you have to remember, because remember, if these guys are, this NADPH, let me write it down here. If the NADPH, okay, this one plus H plus, right? And also like the guys quickly mentioning about this, the NAD plus and the ratio of NADH, right? It's like probably 1,000 times, all right, comparing to the NADPH. That's in your body, right? And comparing to NADP plus with the NADPH, the ratio of this is greater, all right? So basically in your body, we have lots of NAD plus and we have lots of NADPH. So this is obviously this is greater in your body in general. Just wanted to let you guys know that concept also, all right? Now, if you're in the liver cells, right, in your liver cell, if the NADPH, because remember, these guys are, as I said, their role is dependent on where this NADPH are present. If this NADPH are present in liver cells, let's say NADPH are present in the liver cells. So if I say liver cells, right, okay, let's make a liver cell right here, okay? Then one of the things we do with this NADPH is that we use this NADPH for the fatty acid synthesis. All right, fatty acid synthesis, all right, and then after that we also use this for this biosynthesis of cholesterol, all right, and also for the nucleotides and all that stuff. We use that for this one, all right, the fatty acid and cholesterol, biosynthesis nucleotides, we use that NADPH on the liver, if you're talking about the liver cells, right? Now, what else we do? And remember when I was talking about this role of nitric oxide? It's an intracellular mediator for several action, like nitric oxide, like this one, nitric oxide, and it's an intracellular mediator. And what does that do is that, it uses because nitric oxide, what is it? It has a utilized like arginine, right? And arginine is a positive charged amino acid, right? And uses arginine. Let me just write it down that for you. And with the oxygen, with the NADPH, right? And then obviously there's an enzyme required, which is a nitric oxide synthase. In the presence of nitric oxide synthase, right? In the presence of nitric oxide synthase, what do we do with this, right? This nitric oxide is synthesized in the presence of all of this, and then nitric oxide is one of the powerful vasodilator of your blood vessels. And that's what we do, right? Now, what else we do with this? Now, this is for the liver cells, right? Now let's talk about what is the role of this NADPH in the phagocytosis cells? Let's say this is going to be phagocytosis cell, right? It could be like macrophages, right? Let me just write down neutrophils here. I love neutrophils. They're awesome. Neutrophils are like, let's say, macrophage. Okay. All right, and let's talk about what is the role of the NADPH, right? And NADPH is obviously coming from the glucose 6-phosphate dehydrate. I wanted to emphasize on that, right? You know what happens in the phagocytosis? Really, what happens is that there's a very, very important enzyme present in there, and that enzyme is called I'm going to emphasize because this is also very, very important. There's the clinical correlation related with this. This is called NADPH oxidase. All right, guys? What is it? It's called NADPH oxidase. And this is very important enzymes, right? You know what it does is that, you know, whenever there is an inflammation process, right? Basically, the inflammation process, then that's where the neutrophils are recruited, right? Or the macrophages are recruited. And they're on their way. What happens, like sometimes, you know, they can able to generate free radicals. Now, what is free radical? What is the concept of free radicals? Free radicals basically means is that these are called reactive oxygen species. I'm going to write it down. What should I write down? Okay, let me erase this. You got this part, guys, right? All right, let me write it down here because this is very, very important concept, and I want you to understand this really well. Reactive oxygen species. What does that mean? Is that reactive, all right, oxygen species, all right, and they're also called free radicals, all right. Radicals, all right. So what they do is, like, you know, the oxygen, really what happens, this is oxygen, right? Because, you know, remember, oxygens are bound with like hemoglobin, right? That's what it does. What happens is sometimes this oxygen can gain in electrons. Like, for example, if the oxygen can gain 1 electron pairs, then this oxygen will be like this. It basically oxygen with 1 electron pairs, all right? And that is going to be very, very toxic, like this. So if they gain 1 electron, 1 atoms from spontaneously, it could be from like you got too much oxygen, or it could be because of inflammations, or somehow. They extract oxygen, they extract 1 electrons from, let's say, from the iron. So somehow, or it could be from nitric oxide, you know, or sometimes when you go through like radiations, like X-rays, you know, or from water molecules. Let's just say, think about, let's like they were able to, like this oxygen were able to attract 1 pair of electrons. Okay, if they attract 1 pair of electrons, like, what happens? They gain this 1 pair of electrons, right? And the gaining of 1 pair of electrons is what we call the free radicals, and this is very, very toxic for your body because this can cause your DNA damage, guys. It's called DNA fragmentation. They can cause DNA fragmentation, like they can cross-link lipid proteins or lipid membranes. They can do that, right? And which is very, very dangerous for our body, right? And because of that, the hemolytic anemia is also caused by this kind of stuff. But we'll talk about how that will happen in a few seconds. So this is what free radicals or reactive oxygen species means, right? And this is very dangerous. So our body sort of like have to fight for this. So how does this does is like this NADPH oxide, what it does is like it, you know, whenever there's a oxygen, let me put this oxygen here, right? So what it does is during the inflammation process, what happens is that when the oxygen is floating around, this, let me just write down oxygen right here, right? So what this guy does is that it blocks out some electrons from the NADPH. Like, because remember, the NADPH is, I said, it's a reduced agent, right? It's a donor. So it blocks out from there, so it becomes NADPH plus, like, what is this? H plus, right? It blocks out that, and obviously there's going to be NADP plus, right? So when it blocks out that, it'll give electrons, it'll probe, because they'll take 1 electron and put it on the oxygen here. So this will become this electrons right here now. Now this is going to be my free radicals. This is my reactive oxygen species, right? Now this is very, very dangerous, right? But body, you know, our body has like, and guys, this is happening in neutrophils right now, or macrophages, right? And then our body, what it does is that, you know, our body has important mechanism to fight for this, right? And what it does is there is special enzyme located, which is called Superoxide Dismutase. What it does is that it will convert this reactive oxygens and makes a less dangerous molecule, but still dangerous, but less dangerous than this one, which is called hydrogen peroxide, H2O2. All right, this is what, and this is also free radical, but it's less dangerous compared to the this oxygen radicals. And then this oxygens, the H2O2. What happens with this is, you know, there's important enzyme is going to see. This enzyme is called, you know, this is going to be something called myeloperoxidase. All right, and what it does is that it adds a chloride into it too and makes HOCl. What is this compound? These guys is called hypocolorous, right? This is called hypocolorous. It's a dangerous bleach. Because this is utilized to kill your pathogens and bacteria, okay, like foreign bacteria or pathogens or the foreign particles or cell debris that has been ingested by, then gobbled by these macrophages or the neutrophils, right? This was kind of like placed into them. Because of that, this hypocolorous will kill that. Like sometimes guys, in the information process, like what happens is like, if you ask like a patient or to cough, and if you see like a lot of like the green flame, if you see that, then that actually indicative of like, that a lot of neutrophils are present. And the reason why is because of this myeloperoxidase, right? It looks like because it provides this greenish sputum, all right? Just want to let you know this. Now, this is very, very dangerous part because this kills like all this, destruction of microorganisms. That's what this guy does, and that's called hypocolorous. Now, one of the things you have to understand is that guys, let's say you have this NADPH oxidase deficiency, right? So if you have NADPH oxidase deficiency, then what would I able to make the reactive oxygen species? And we kind of want to make a reactive oxygen species too, and then we have to have this pathway run into it so we can kill this pathogens and microbes too. But if I don't have these enzymes, I'm not going to able to make that. Okay, if I'm not going to be able to make reactive oxygen, I'm not going to be able to make this hydrogen peroxide, right? So that means I'm not going to be able to kill those foreign the cell debris or the pathogens and foreign bacteria, right? Then I'm going to have these problems. And what is that problem is going to cause? Like, because remember, this is very important. If you have a deficiency on this call, which is a genetic deficiency, right? This is called genetic deficiency. All right? There is a name for this, which is called, what is this? Chronic, all right? The it's called chronic granulomatous, granulomatous disease. This is important disease, right? This has to do with the NADPH oxidase, and with this, people who have this kind of stuff, obviously they will, obviously look, this is immunocompromised, right? Immunodeficiency, this guy. What does this mean? Which basically means is that, sorry for the spelling, but basically immunodeficiency basically means these guys are very susceptible to like infections. There will be persistent or severe infection all the time because they don't have the molecule to fight for their infections, right? But guys, this is immunodeficiency. But remember, even with the glucose 6-phosphate too, you're not going to make NADPH. I mean, you will make probably NADPH, but then you probably have this compound, but actually you won't. So in this also case, you also have immunodeficiency. But what makes it different with the glucose 6-phosphate dehydrogenase deficiency with the NADPH oxidase deficiency? That's something that you have to understand, because in both the cases you're going to have immunodeficiency or immunocompromise. All right, they're both in the condition they're very susceptible to getting infections very, very quickly, persistent severe infection. Right? Difference is this: these guys will have hemolytic anemia and also Heinz bodies, and we'll talk about what that means. All right, so that's what makes it this guy the NADPH oxidase difference from the G6P dehydrogenase deficiency, right? And this is all happening in the phagocytosis cells, right? And then if the phagocytic cells are not able to generate this, what is it called? It's called superoxide. Then there's a test they do. This is called NBT test. Like NBT test too, which is basically it's called nitrobol tetrazole. It's called nitrobol tetrazoleum test, and which usually turn out to be negative. That's what they do this test in order to figure out this thing. All right. Now we have to. Now this is what I want to talk about. The emphasis on your neutrophils. Right now let's talk about what is the NADPH role in the erythrocytes. That is also very, very important. We have to talk about, right? Now I'm going to make this red blood cells, and we'll talk about what is happening. What is the role of this NADPH on the red blood cells. Remember, do you guys know what's the size of the red blood cells? Like 7 to 8 microns. All right? That's the size of my red blood cells. All right, now, look, this is red blood cells, right? Okay, quickly, what's gonna happen? Quickly gonna talk about this thing. So what is gonna happen is obviously you have a glucose, right? And then from the glucose, what are you making? You're making glucose 6-phosphate, right? Now, this is what is happening in red blood cells, right? And red blood cells are enucleated cells, right? Doesn't have a nucleus and all that. Now, from the glucose 6-phosphate, obviously, major enzyme, which is going to be my glucose 6-phosphate dehydrogenases, right? So now, let me write down this glucose 6-phosphate dehydrogenase enzyme right here, right? And what is this guy is doing? It is basically going to, look, take electrons from glucose 6-phosphate right here, right? And then give it to this guy. So this is going to be obviously, let's make this as NADP plus. I'm going to give it to this guy, who's going to be NADPH plus H plus. All right? This is what is happening here, right? Now what is going to happen here is that, guys, there's a very important enzymes here, which is called glutathione. It's called GLUTA, glutathione reductase. All right, reductase. All right, then. Quickly tell you about what is glutathione is. It's a tripeptide amino acid. Which basically means is like, come back here. You have a glutamate, all right, glutamate, plus you have a cysteine, plus you have a glycine, all right. All together combined, you make this glutathione, all right. And glutathione is very important because glutathione is what is going to help protect yourself from. This is going to help protect. This glutathione is going to help protect cell from H2O2. All right. So basically, that's what it is. So when you have this glutathione reductase, what it's going to do? It's going to take this thing, guys, this compound right here, right? So let's make this, and then make it this way. So take it here, and then pluck it out, and then give it to something else. Actually, it's going to give it to this guy, which is GSH. What does that mean? What it basically means is that because taking out from here, all right, and giving to this guy, which basically means that actually it's going to get you're going to make 2 G and SH, right? From there plucking out. So this is my reducing agent now. What is this called? This is called my reduced glutathione. All right, this is because this is very important, because this reduced glutathione, and we're making 2 of them, all right, because this reduced glutathione is what going to donate the electrons to actually the hydrogen peroxide. And once you donate the hydrogen peroxide, you know, it can convert into the harmless water, because remember, hydrogen peroxide is also free radicals, all right? So this is going to this, and hydrogen peroxide doesn't care where the electrons coming from. It just requires 2 electrons to make water, right? So that's what these guys are doing. But now we have to talk about where the free radicals are coming from, though, before even we talk about this one. All right, now what I'm going to talk about is right here, the reactive oxidant space. Where is this coming from? Okay, we're going to talk about this reactive oxidant. The reactive oxidant is coming from, like, as I said, multiple things. It could come from radiation, it could become from inflammations, all right. It could become from here, like basically what happens is that, look, what happens is that, let's say, if I make this, let's say my mitochondria, right? And what happens whenever we take the oxygen, right? What happens? It goes to the lungs, right? And then from the lungs, what happens? From the capillary beds, and later from the cells, it comes the mitochondria, right? And from really what happens, this oxygen is carried in where? Oxygen are carried from in the 4 pockets, right? Because with the hemoglobin, right? Hemoglobin, you know, the Fe plus 2 plus state, right? And then you have oxygen are sitting onto this oxygen here, right? Oxygen here, Fe2 plus and Fe2 plus, right? All this. So basic oxygens are carrying in my hemoglobin, right? And that's why we say 100% saturated oxygen. Sometimes what happens is that this oxygen can actually gain in electrons. Actually, spontaneously taking electrons from this Fe2 plus this iron also. And if they took an electron, just needs 1 electrons to make the reactive oxygen species. You can make the 1 from there. Other thing they can take electrons from is reacting oxygen. They can take it as they are passing, when they're going, and then when they're going to the tissues, mitochondria or like cells, when they're past lipid bilayer membranes, and where they're actually they're leaving their oxygen to the tissue. Sometimes they're with the lipid membranes and all, they could gain like extra electrons there too, all right? So from the bilateral of the your cells, is it possible they could get electrons from there as well? Especially in the mitochondria, right? Especially like from the, it could be because like from electron transfer chains, also they could gain from there too, because remember, you have O2 and you just have to have 4 electrons to make water. That's how, like, you know, this is how like you're making water in the electron transfer chain, right? So you just need extra 1. They could pick out of from here to make like O2 minus. Oh, sorry, O2 with the 1 electron pair. So that's what I want to emphasize on. But the key point here is that, let's say these guys got an electrons from this pocket, which is spontaneously they got an electrons, right? So if they got it from the, let's say, iron state, which is going to be my here. So if I do this, let's say this is going to be like Fe2 plus state, right, of the hemoglobin, correct? If it got it from here, like what happens is that if we get oxygens from here, it could become 1. It could become radicals from here, which is a reactive oxygen, or it could be also called met hemoglobin, right? So this is called met hemoglobin, right, guys? If you have, and usually every single day, I think it's like 3 to like 5% of met hemoglobin is generated. And remember, when you make the met hemoglobin, what happens is that met hemoglobin cannot carry oxygens, right? So this, somehow the body has to have a mechanism to fight for this, all right? So there is a body obviously there's an enzyme which is called met hemoglobin reductase enzyme is there. What it does is like, because it gain 1 electrons, right? So this become a 3 state. So because this met hemoglobin reductase enzyme is present there, it will convert back into met 2 plus state in the hemoglobin. Because remember, if this met hemoglobin is higher in percentage, more than normal, then it cannot carry oxygen, then your whole body will be bluish. This person will cyanosis. We have a whole blue bodies, right? If you have a high amount of met hemoglobin. And sometimes there is a deficiency on the met hemoglobin too. If you have deficiency on this met hemoglobin reductase, then sometimes what they give this something called methane blue. You can give something called methane blue. All right, if they give methane blue, really what happens is because look, I just need an electrons, right? This one to be in the Fe2 plus state. So because of that, like, you know, it will be in the it will reduce and become the Fe2 plus state. So then it will start carrying oxygen again, and methane blue can provide the electrons that this hemoglobin requires, right? Now, even with the free radicals too, like there's a body, like, you know, our body can the body has these mechanisms to fight for this. You know, whenever there's like whenever there's radicals are present there, you know, we call this case called oxidative stress. I think oxidant stress. All right. And then bunch of things can actually give out like having a lot of free radical species, like for example antimicrobial drugs. One is, I'm just writing some of this, okay? Antimicrobial drugs. One is like radiations. All right, radiations could be that. One could be inflammations. All right, one could be like nitric oxide. They could do it. And there's something called Fava beans, guys. Infections, obviously. And then something called Fava beans. Actually, have you ever heard this, guys? These Fava beans is also very. If you're taking this in diet, you can actually take this lots of like if you're having in this because it contains a lot of oxidant, so you could have you could get this reactive oxygen species like very commonly. All right, so it's very important that you probably like limit taking this. Also, like, you know, some of the things like you have streptomycin antibiotic if you do that, or some of the things like, you know, if you are taking the anti-malaria drugs like QUI and quinine drugs, all right, that could be do. And also other thing is called nitrofurans. furans, right? And this is like a anti-microbial drugs, right? Because they can actually increase your oxidant, and then which can actually increase your reactive oxidant species, right? And your body has to fight for this too. And our bodies, like your diet is very important actually to fight for this reactive oxidant species. Like for example, especially your vitamin, like your vitamin A, E, and C, and then B carotene. These are, sorry for the spelling, but these are very, very important for fighting for this for your reactive oxidant species, right? So the vitamins are very important for that, or your diet, that kind of species. Now, let me just erase this. This is oxidant stress right now. Now coming back to this again, sorry, just went there. So let's say this oxidant, you have this free radical you generate from there, right? So what happens is that when the reactive oxidant comes in here, right? Let's say this is my O2 with the electrons here. Obviously, remember with the O2, what's going to happen is there's an important enzyme called this enzyme is called superoxide dismutase. Like superoxide dismutase, what it does is that it kind of like converts this free radicals into this less harmless thing, which is going to be my hydrogen peroxide. You remember this, guys? Yeah, right? Now, this hydrogen peroxide loves electrons. It does love electrons. What it does is this is, remember this, I said the 2G, and this is sulfur hydride. The sulfur hydride is very important because remember, guys, I told you this, this glutathione is coming from like glutamate, cysteine, glycine. This cysteine is very important because this is what the sulfur is coming from. Remember cysteine residues, like sulfur hydride? That's why, because the cysteine is donating that. Okay, that's where this SH group is coming, and we're making 2 of them because your hydrogen peroxide requires 2 of them, right? So when this gives out to this guy right here, all right, and obviously in the presence of this important thing, which is called, I'm going to write it down here, which is called, let's say, glutathione and peroxidase, I think it's called, right? Peroxidase. What happens is that you make this water right here, right? And then obviously when this happens, what do you make this important compounds here, which is a glutathione sulfur, and then obviously with the sulfur glutathione you make the breeze gap onto this, and this path will keep going and keep going. And once you have this one, this we call this as oxidative, right? Because this is a reductase, right? So you can call it as oxidative glutathione, you can say this, right? You can call this an oxidative glutathione, and this is a reduced glutathione here. Reduced glutathione is very, very important, right? Now this is what, and then this is keep happening to detoxify the superoxide or the free radicals, right? This is keep happening, and then obviously your NADPH plays a huge role, and you see how this NADPs are playing a role into this one, right? Now let's quickly talk about what happens if there is a reduced glutathione. Okay, reduce this glutathione. You have, let's say, you have a G6PD deficiency, right? Or somehow your NADPH is deficiency, right? So if in that case, what happens, guys, like you're not going to make the reduced glutathione. So if you're not going to make a reduced glutathione, then can I able to donate electrons to hydrogen peroxide and make it water? No. So if I'm not able to do that, what is going to happen is that in red blood cells, and this is my red blood cells, right? What happens is that level of this hydrogen peroxide, I'm going to make this in red, right? It's going to go up like really, really high, right? So when you have this hydrogen peroxide level goes very, very up, very, very high, what happens? This hydrogen peroxide will start like taking electrons from hemoglobin. Okay, this will take, look, HO2, when you have a high level of HO2, it will start taking electrons from hemoglobin, right? And when you start taking the hemoglobin, what is going to happen to the hemoglobin, right? Causing, once I take the hemoglobin to cross-link. Okay, that's a cross-link, it causes a cross-link of hemoglobin, right? That's what will happen. And when the cross-link happens, what is going to happen with the cross-link? The hemoglobin cross-linked actually can bind and break the cell membrane. Like it can bind here and it can break this all cell membrane. When it bind and break all the cell membrane, what is that called? That is called hemolytic anemia. All right, that is going to call hemolytic anemia. And then what also does is that this hemoglobin can get denatured, right? When it gets denatured or it becomes like precipitated, then it becomes what? That we call them as a Heinz bodies. All right, that's what called Heinz bodies, right? That's what it's called. And obviously you're not making the NADPH, so obviously these people will be also immunodeficient. immunocompromised, which basically means that these guys are very, very susceptible to like infections. Okay, so these are 3 triad that you always see when you have a G6PDH deficiency. Glucose 6-phosphate, what is this? Like glucose 6-phosphate dehydrogenase deficiency, you're always going to see this triad. And remember, guys, the glucose 6-phosphate this deficiency is very, very common. Actually, it has happened to up to like 400 million people worldwide, and this is going to be X-linked recessive inheritance. Because why this is called is because if you look at this condition, what happens is that there are 300 different mutation that has occurred in the X-linked encoding G6PD. Okay, and these are these are usually like very, very like common with like certain type of people, like usually in like Africa or Middle East, Middle East people, and then also like South Asia. These are very, very these are places where you get to see like people with this deficiency. And then if you want to do like a test to diagnose the glucose 6-phosphate, you gotta look for the red blood cells count, you gotta look for the reticulocyte, and then blood film to look for the Heinz bodies, right? Because it's important to look for the Heinz body, because with this deficiency, it will create unstable enzymes. Okay, and then obviously it's going to have a lot shorter like half-life. Okay, and obviously there's a glutathione is not there, so obviously it's not going to fight for the cell membranes and all that stuff. All right, now one more thing that I also wanted to actually emphasize you guys on is that this glutathione, this oxidative glutathione, right? One of the things I think you should remember, this is a role of selenium. Selenium is also kind of like used here, like down here. But you know, this selenium, it's actually a little bit of selenium is used, but you don't want to use selenium a lot, or you don't want to take selenium supplement, because that could actually cause a huge problem, because selenium toxicity can kill you, because you could have nail discolorations and all that stuff. All right, but that is also, this selenium is sometimes considered as like your antioxidant. But even though it is called that, but you don't want to use on your diet. All right, that's something that I wanted to emphasize onto that too. We talked about a lot of things against, like how do you fight for the reactive oxygen species. I'm just like quickly checking, make sure that like I've covered like almost everything that I was supposed to cover, right? And then one of the things also, like this glucose, the glucose 6-phosphate deficiency, individuals are resistant to malaria. Actually, common in certain parts in the world, caused by this parasite called Plasmodium. It's called Plasmodium, right? With this fel, which is going to be falciparum. All right, that's something that I also wanted to mention about this. So whenever you have, as I said, whenever you have, let's say, the glucose 6-phosphate deficiency, obviously you're going to have a reduced NADPH, right? Which means you're going to have reduced glutathione, right? Because remember, you're not making glutathione, right? So you have reduced glutathione. That means what you're going to have increased sensitivity to oxidative. Because remember, this is going to be what? Oxidative stress, we call them, right? So you have increase in oxidative stress, right? You're going to have a hands body formations, and also you're going to have a hemolysis, right? So that's why the hemolytic anemia will happen, right? So we'll talk about that. Talk about, like, you know, it's very prevalent. It's excellent recessive, right? We talked about that. Talked about the chronic granulomatous and all that stuff. All right, guys, this is it for now. I hope that I made it very, very clear to you guys, and I hope it helped. I hope I was able to help you guys. All right, thank you, and you have a wonderful day. Thank you.